Let me start. Welcome everyone to the Informs Optimization Society's virtual conference. As you know, our regular in-person conference that usually takes place around this time of the year is postponed twice due to the pandemic. But I'm happy to mention that 2020 conference, which we all sincerely hope to be in person, is confirmed. It is going to be during March 13th to 15th, 2022 in Greenville. And we're going to publish it online and registration shortly, information shortly. So today, I'm very pleased to introduce our first plenary speaker of our virtual conference, Professor Daniel Kuhn. Professor Kuhn is the chair of Risk Analytics and Optimization at EPFL. His research interests are in data optimization, data-driven optimization, the development of efficient and computational methods for the solution of stochastic and robust optimization problems, and the design of approximation schemes that ensure their computational tractability. Professor Kuhn serves as the area editor for continuous optimization for operations research and as an associate editor for several journals in our field, including the management science, mathematical programming, math of OR, and operations research letters. Professor Kuhn is also the winner of the 2021 Lanchester Prize, along with his co-author Payman Esfahani for their 2018 math programming paper entitled Data-Driven Distribution Robust Optimization using the Wasserstein metric, performance guarantees, and tractable reformulations. So today's talk has the title, A General Framework for Optimal Data-Driven Optimization. And Daniel, please, the virtual floor is all yours.
Thank you very much, Aldo, for the kind introduction, and I would like to thank the Informs Optimization Society very much for inviting me to give this talk. It's a great honor for me.
So, Daniel, I'm sorry, I forgot to mention one thing. I apologize for interrupting you. Yeah. So there we will, at the end of the talk, there is going to be a Q&A session planned. So if you have questions, if you could please click on the Q&A button at the end of your screen, at the end towards the bottom of your screen, and type in your questions in there. You can do it during the talk or after the talk, and I will read them. I'm not sure how many of them we will get, but I will try to read as many as possible and then pose the questions to Daniel. Thank you. Sorry for the interruption.
No worries. So my talk is based on joint work with my postdoc Tobias Suter and with Bart van Paris from MIT. So what I would like to do in this talk is to construct data-driven solutions for stochastic optimization problems that make, in some sense, the best possible use of the available data. So that means that I would like to construct estimators that are optimal or efficient in some sense for the optimal values as well as the minimizers of data-driven stochastic optimization problems. So I'd like to address this challenge in a well-defined framework that is general enough to support interesting applications. So this framework consists of three primitives, and the first one is a stochastic optimization problem that represents the ground truth against which the estimators we're going to construct will be assessed. The second primitive is a family of probability measures that capture prior structural information. And the third primitive is a stochastic process that generates training samples. So let me first talk a bit about the stochastic optimization problem. Here, the goal is to minimize a generic objective function that depends on the probability measure that governs the uncertain problem parameters. So examples of this objective function include the expected value or some risk measure of an uncertain loss function. Another example would be the conditional expectation of an uncertain loss function given contextual information. Or a fourth example might be the long-run average expected loss of a parametric control policy. There are many other objective functions that would fit our framework. These are just examples. Now, the crux of data-driven optimization is that the probability measure that underlies our stochastic optimization problem is not known. However, throughout the talk, I'm going to assume that this probability measure is known to belong to a parametric family. So actually, all probability measures in this parametric family will be defined on the same sample space. And I'm going to assume that these probability measures are parameterized by a finite dimensional parameter vector theta that ranges over a convex set capital theta. Now, even though the true probability measure, and in particular the parameter theta that encodes this, is not known, we assume that we have access to a finite trajectory of a stochastic process that generates training samples that provide statistical information about the unknown theta. Now, examples of data-generating stochastic processes that we will consider in this talk include processes of independent and identically distributed observations on a finite state space, finite state Markov chains, also several classes of vector autoregressive processes, or i.i.d. processes where each observation belongs to some parametric distribution function, class of distribution functions like normal distributions or exponential distributions, etc. So again, there are many more examples that would fit the framework. What I would like to highlight at this point is that by considering also Markov chains and autoregressive processes, we do not insist that the training samples are independent. So we actually explicitly allow for serial dependencies in our data. Okay, throughout the talk, I would like to use the following color coding. So I use black symbols to denote known deterministic quantities. I will use red symbols to denote unobservable quantities, and I will use blue symbols to denote observable functions of the training samples. So these are accessible to the decision maker. Now, to make things a bit more concrete, let me give you a simple example of our general framework. So I would like to look at the data-driven Newsvendor problem. So the Newsvendor problem captures the fundamental dilemma of a seller of a perishable good. And textbook example of such a perishable good is a newspaper which becomes worthless at the end of the day. So let me first describe the stochastic optimization problem. So at the beginning of the day, a newsvendor decides on the quantity X of newspapers that are bought from the publisher. So I'm going to assume here that X can be any integer between 1 and t. During the day, an uncertain demand psi is revealed, and I'm going to assume also that the demand may take any value any integer value between 1 and t. Then during the day, the newsvendor will sell newspapers until either the inventory or the demand is exhausted, and that means that the sales quantity is actually just the minimum of X and Xi. The goal is to minimize expected costs, and the expected cost function is shown here. It depends on the wholesale price, which is the price that the newsvendor needs to pay to the publisher, and on the retail price, which is the price at which newspapers can be sold on the market. So this one should be higher than the wholesale price. And the cost function involves includes the ordering cost, which is just the product of the wholesale price times the order quantity, and it involves minus the profit of sales, which is the retail price multiplied by the sales quantity. Here, the expectation is evaluated with respect to the distribution of the uncertain demand, which is denoted by theta. Now, theta is not known. However, we have access to historical demand data from which we can learn theta. So more concretely, I assume that we have access to training samples psi t, historical demands that are generated by some stochastic process. Now, the probability measure that governs this stochastic process is unknown, but it is known to belong to a parametric family. And in particular, I'm going to assume that the training samples will be independent and identically distributed under every of these probability measures. And I'm also going to assume that the vector theta that encodes the probability measures represents the demand distribution. So it represents a d-dimensional vector whose components correspond to the probabilities of the different demand levels. So in this setting, the Newsvendor would like to solve the true stochastic optimization problem. This is not possible because the theta is not known. However, the training samples are available, and so what needs to be done is the Newsvendor needs to construct a surrogate optimization problem that is solely constructed from the training samples, but does not depend on the theta. Okay, so that's just an example of the setting. So let me now talk about how we can construct, in general, such surrogate optimization models. So remember that our true goal is to solve the original stochastic optimization problem. This is not possible because the parameter theta that encodes the true probability measure is not known to us. Instead, we have access to t training samples generated by our stochastic process. Now, to construct the surrogate optimization problem, the simplest thing we could do is we could use some methods from statistics to map the training samples to some statistic here denoted by theta hat t. And it's maybe best to think of theta hat t as an estimator for the unknown theta. And the easiest thing we could do is we could just substitute this estimator into the objective function, replacing the unknown theta. This will give us a surrogate optimization problem. However, I would like to adopt a more general view in this talk. So I would like to allow for surrogate optimization problems that are constructed directly from the data, without the detour of first constructing a statistic or an estimator. So I would like to abandon this separation of estimation and optimization, where I first need to find an estimator and only then can solve an optimization problem that depends on the data only on the estimator, through the estimator. Now, how can we construct such the objective functions of such a general surrogate optimization problem? Well, there is a huge literature on how you could do that, and the very most widely studied approach is the sample average approximation, which essentially just replaces the unknown true probability measure in the objective function with the empirical distribution on the training samples. Now, some people have argued that you could do better by adding a regularization term to this empirical objective function, and the hope would be that this will result in better out-of-sample performance. Another approach is the predict and optimize approach, which just substitutes some estimator constructed from the data into the true objective function, which is exactly what I've shown you on the previous slide. But then you could either construct your estimator, you can train your estimator in view of a generic loss function like the mean squared error, or you could also train it in view of the optimization problem you would actually want to solve eventually, be a bit more smart about it. Probably you could also use some neural network model to that maps the training samples to the objective function of the surrogate optimization model, or you could use methods from distributionally robust optimization. So here you use the training samples to construct a family of distributions or an ambiguity set, such that under each of these distributions the training samples are in some sense sufficiently likely. And then the objective, the surrogate optimization problem, just evaluates the worst case objective, where the worst case is taken with respect to all distributions in the ambiguity set. Now, here again, there are really numerous different methods for how you construct the ambiguity set from the data. And so the question is really, how could you do it maybe in the best possible way? So in the remainder of the talk, I would like to use the following terminology. So throughout, I'm going to denote the objective function of our surrogate optimization problem as a data-driven predictor, because it predicts the objective function of any fixed decision in view of the training samples. And of course, every data-driven predictor determines a surrogate optimization problem. The predictor is the objective function of the surrogate optimization problem. And any minimizer of the surrogate optimization problem will be called a data-driven prescriptor, because it prescribes a certain feasible action that is somehow constructed from the data. So I would like to point out at this point that our notion of data-driven prescriptor is extremely general, because really any function that maps the training samples to a feasible decision can be understood as the minimizer of some data-driven prescriptor. That is always possible. So by looking at such prescriptors, we really look at arbitrary data-driven decisions, arbitrary feasible decisions as functions of data. Now, the goal will be to construct these data-driven predictors and prescriptors in some sense in an optimal way. Now, in order to compare different predictors and prescriptors, I'm going to use certain performance measures. So the first of these performance measures is the in-sample risk, which is just the optimal value of the surrogate optimization problem, or its objective function evaluated at the minimizer. The in-sample risk is accessible to the decision maker because it is only a function of the training samples, which are known. The second performance measure is the out-of-sample risk, which is the objective function value of the prescriptor in the true problem. This is the actual quantity of interest. However, it is not accessible to the decision maker because it depends on the unknown parameter vector that encodes the true probability measure. Now, I would like to emphasize that any prescriptor x hat t may be induced by many different data-driven predictors, c hat t. And our definition of the in-sample risk depends on the particular choice of c hat t. So in particular, c hat t could just be shifted by a constant without affecting the prescriptor x hat t. And this shows to you that minimizing the in-sample risk instead of the out-of-sample risk is nonsensical unless we restrict the choice of the predictor c hat t. So to this end, I would like to propose a third performance measure, which I call the out-of-sample disappointment. So this is just the probability under the unknown true probability measure that the out-of-sample risk strictly exceeds the in-sample risk. Now you can imagine that if the out-of-sample disappointment is large, this means that the true risk of our prescriptor x hat t is larger than the predicted risk of our prescriptor. And that lulls the decision maker into a false sense of security and really leads to disappointment in out-of-sample tests. So ideally, you would like all of these three performance measures to be as small as possible. However, this is not possible because there is a fundamental trade-off between the in-sample risk and the out-of-sample disappointment. From the definitions, it's clear that if I decrease the in-sample risk, for example, by just adding a negative constant to the corresponding data-driven predictor, then this will increase the out-of-sample disappointment and vice versa. So it should be challenging to minimize these two performance measures at the same time. So let's quickly go back to our Newsvendor problem and let's study this trade-off between in-sample risk and out-of-sample disappointment for several surrogate optimization models that have been proposed in the literature. So the left panel on this slide will show how the out-of-sample disappointment depends on the number of demand samples. The middle chart will show how the in-sample risk depends on the number of demand samples. And the right chart will show the trade-off between the in-sample risk and the out-of-sample disappointment. So a particular surrogate optimization model will be represented by a point in this plane where the x-coordinate will be the exponential decay rate of the out-of-sample disappointment. Now, because we want the out-of-sample disappointment to be small, a high decay rate is good, is better. The y-coordinate in this plane will be the asymptotic in-sample risk, and this one will want to be as small as possible. And I'm also going to assume in this example that the true demand distribution is uniform, but the models, of course, they don't know that. It's just how I generate the data. So the first model I would like to study is the sample average approximation, which evaluates the expected Newsvendor cost under the empirical demand distribution, which is denoted by theta hat t here. So you can see that the out-of-sample disappointment converges to 1/2 under this model, and this can be explained by the central limit theorem. So the out-of-sample disappointment does not decay at all. The in-sample risk converges quickly to, or saturates quickly as the number of samples increase to a relatively low value. And the dot here on the right-hand side represents the SAA model So you can see that the decay rate of the out-of-sample disappointment is 0 here because the out-of-sample disappointment does not decay for this particular model. Now, if we would like this disappointment to decay, a simple remedy would be to add a positive bias term to the SAE objective. So the dashed line in the right chart shows the trade-off between the decay rate of the out-of-sample disappointment and the in-sample risk as this parameter R is swept from 0 to infinity. It's clear that if R is 0, we just recover the SAA model. If R increases, we obtain a more conservative model. So we overestimate the true cost. This means that the out-of-sample disappointment will decay and the decay rate will become positive, but at the expense of a higher in-sample risk. So let's look at the perhaps more interesting model, which is a distributionally robust optimization model with a moment ambiguity set. So here, the data-driven predictor just evaluates the worst case expected cost over all distributions that share the same first 4 moments as the empirical demand distribution up to some threshold R. And it's clear, the bigger R, the bigger the ambiguity set, and the more conservative is a predictor. So if the R, so I would like to show you I would like to show you what happens for 3 different values of R, a small one shown in green here, a medium value shown in light blue, and a large value shown in dark blue here. So in all 3 cases, you see on the left-hand side that the out-of-sample disappointment does decay this time. This is a log scale, so we have an exponential decay. You see that the more conservative the model, the higher the in-sample risk, but it saturates still very quickly. And on the right-hand side, we see the trade-off between these 2 quantities asymptotically. Now, if I sweep the parameter R from 0 to plus infinity, then all these models will trace out the dashed blue line in the right chart. So again, the higher, the lower the out-of-sample disappointment, the higher the in-sample risk. There is a basic trade-off. Let's look at the 4th model. This is another distributional robust optimization model with a Wasserstein ambiguity set. So here we evaluate the worst case expected loss over all distributions in a ball around the empirical demand distribution. And the radius of this ball is R. And we measure distances between distributions by using the Wasserstein distance. So I've picked a particular value of R for which the out-of-sample disappointment decays as fast as for the dark blue model that emerged from the moment-based DRO model. But we can see that even though we have the same out-of-sample disappointment, the in-sample risk is lower. So in that sense, it offers a better trade-off. Now, if we sweep R in this model, then all the different predictors that trace out the orange dashed line in the right chart. If R is 0, the ambiguity set here just contains the empirical distribution, and so we just recover the SAA model. But if R increases, then we have the usual trade-off. What is interesting to see is that for any fixed decay rate of the out-of-sample disappointment, the Wasserstein models, they offer the lower in-sample risk than the other models we've seen so far. Let's look at the 5th model, which is the same as the Wasserstein DRO model. So it evaluates the worst case expected cost over a ball of radius R, but this time we use the Kuhlbach-Leibler divergence instead of the Wasserstein metric to measure distances. So in red, I show you a particular choice of R for which the out-of-sample disappointment decays faster than anything else we've seen before. However, the in-sample risk saturates at a point that is lower than several of the models we've seen before. Again, if I trace out R from 0 to infinity, then I get the red dashed line in the right chart. And this shows us that actually the KL divergence-based distributional robust optimization model offers a better trade-off between in-sample risk and out-of-sample disappointment than any of the other models we've seen. So this is the last model I wanted to show to you. What we see here is that different predictors can display quite a different performance. And the other thing that I would like to point out is that for all the models we've seen, the out-of-sample disappointment followed almost a perfect straight line on a log scale, which means that the out-of-sample disappointment is really almost perfectly described by the exponential decay rate of this quantity. So now let me try to argue that, let me try to explain how we could potentially find optimal predictors and prescriptors and thereby optimal surrogate optimization models. So the actual quantity we would like to minimize is the out-of-sample risk. So we'd like to construct a prescriptor x at t that has smallest possible out-of-sample risk. Now the out-of-sample risk, because our prescriptor is feasible, will always be larger than the theoretical minimum, which is the optimal value of the true stochastic optimization problem. Now, if we focus attention on prescriptors that have a small out-of-sample disappointment, then the in-sample risk will be higher than the out-of-sample risk with high probability, and therefore also the expected in-sample risk will be very likely higher than the out-of-sample risk. So our goal now is to find predictors and prescriptors that have a small in-sample risk, but at the same time we would like to maintain a small out-of-sample disappointment so that the in-sample risk stays above the out-of-sample risk. And graphically, this means we try to push down the expected in-sample risk, and thereby we will indirectly also push down or minimize the out-of-sample risk. This is what we would like to do. Now, of course, the same data-driven prescriptors may perform very differently or may display very different out-of-sample risks under different models. In fact, there are infinitely many possible different models, and so it's best to think of the out-of-sample risk as a continuous function of theta. Also, the theoretical minimum, so the true minimum of the original stochastic optimization problem depends on the theta, it depends on what the true distribution is. And also, the expected in-sample risk depends on theta, which encodes the probability measure under which we take the expectation. Now, if we do not know which theta is the true one, we could try to construct predictors and prescriptors that have a small in-sample risk under every possible model, while maintaining a small out-of-sample disappointment also under every possible model. If we do that, then we would graphically try to push down the in-sample risk simultaneously for all theta, because we maintain a low in-sample risk, the out-of-sample, because we maintain a small out-of-sample disappointment, the out-of-sample risk will stay underneath the in-sample risk, and we will therefore also uniformly minimize it for all theta, and therefore hopefully also for the unknown true theta. So let me formalize this. So I would like to construct an optimization problem to find the best possible predictors and prescriptors. Now, remember that these are functions of the T training samples. So these are complicated objects, and this is a complicated functional optimization problem. Also, we would like to choose these predictors and prescriptors so as to simultaneously, for all models theta, to minimize the in-sample risk. So we end up with a multi-objective optimization problem with infinitely many objective functions, one for each possible true probability measure. Now, the constraints in this model here, they are meant to ensure that the out-of-sample disappointment remains small under every model theta. This can be seen by multiplying the sample size t here to the right-hand side and exponentiating both sides. So if you do that, then you see that the constraints essentially says that the out-of-sample disappointment, which is this probability here, should be smaller or equal to e to the minus RT. So it should decay exponentially at rate R with the sample size t, asymptotically as the sample size grows. So multi-objective optimization problems, they are somewhat difficult, right? If we try to minimize the objective function, so the in-sample risk for one particular theta, say theta 1, then it may well happen that in doing so, we will at the same time deteriorate another objective function, maybe the one corresponding to theta 6. So in a multi-objective optimization problem, we should therefore be very lucky if we manage to find a solution that simultaneously minimizes all the objective functions. So all the objective functions for each theta. If we find such a solution, then we will call it a Pareto-Dominant solution, because it contains the best possible trade-off between in-sample risk and out-of-sample disappointment for all possible models theta, and therefore, in particular, also for the unknown true theta. So it'd be very great if you could find such a Pareto-dominant solution. But we should not generally expect it to exist in multi-objective optimization problems. So the optimization problem over predictors and prescriptors here, it really optimizes over, so basically each predictor encodes a surrogate optimization problem. So this model here optimizes over different optimization models, and therefore we can interpret it as a meta-optimization problem, an optimization problem over optimization problems. And this meta-optimization problem has several strengths. So one of them is that, as I've shown to you, it represents a proxy for optimizing the out-of-sample risk, which is the actual quantity of interest, but for which I do not know how I can actually minimize it. It errs on the side of caution, so it results in predictors that are pessimistically or conservatively biased, which is usually perceived as a good thing because it leads to better generalization properties. The key benefit of this meta-optimization problem, as I'm going to show to you, is that it admits a Pareto-dominant solution in closed form. So we're very lucky that such a Pareto-dominant solution does actually exist for this model. I will also show to you that it facilitates actually a separation between estimation and optimization. The model also has some weaknesses, like any model. In this case here, the performance criteria we're optimizing are asymptotic. So in the objective, we have the asymptotic in-sample risk, and in the constraints, the asymptotic exponential decay rate of the out-of-sample disappointment. However, this is maybe not so big of a problem because we have seen in the example before that the out-of-sample disappointment really traces out, for all models we've seen, an almost perfect straight line on a log scale. So actually, the exponential decay rate captures this out-of-sample disappointment very accurately. Also, the choice of the threshold R here is to some extent arbitrary, right? This R should be seen as sort of a risk aversion coefficient or a regularization coefficient or hyperparameter. And the choice of it is subjective. The benefit, however, is that this R, unlike regularization parameters in other statistical models, has a precise physical meaning. It represents the rate at which the out-of-sample disappointment decays with the number of training samples. So this is a precise meaning. We know what it is. Also, you could ask, why do we insist on an exponential decay here? We could ask for a faster or slower decay, and this may be something we may want to talk about later. Another possible weakness is that any optimal or even every feasible model is biased, is conservatively biased. But okay, let's work with that model and see what we can say about it. So actually, I would like to show to you that this model admits under interesting conditions a Pareto-dominant solution. But before I do that, I would like to study a somewhat simpler model that is easier to solve. Also for didactic reasons, that's better. So remember that the predictors and prescriptors, they're just functions of the t-training samples. And just processing or even storing such functions may become impractical when the sample size t becomes large. So therefore, it seems natural that we could simplify the problem by compressing these t-training samples into a summary statistic, theta hat t, that has constant dimension. And then, instead of looking at predictors and prescriptors that depend on the training samples directly, we could look at predictors and prescriptors that depend on the training samples only indirectly through this summary statistic. So I will refer to these as compressed predictors and prescriptors because they compress the training samples into the summary statistic of constant dimension. And then I can also define a restricted meta-optimization problem, which does not optimize over all predictors, prescriptors, or over all functions of the training samples, but only over much simpler functions that depend on the training samples indirectly through the statistic theta hat t. Now, I would like to show to you that this restricted meta-optimization problem has a Pareto-dominant solution if the summary statistic theta hat t satisfies a large deviation principle. And I would like to remind you first what the large deviation principle is. So we say that an estimator theta hat t satisfies a large deviation principle if there exists a rate function I, such that the inequalities shown on this slide hold for every possible Borel set D. Now, this rate function I should be seen as sort of a distance measure between a realization theta prime of our estimator, theta hat T, and the unknown true model of theta. Now, what do these inequalities say here? So actually, on the left-hand side, in both the inequalities, we essentially have the exponential decay rate of the probability that the estimator, theta hat T, falls into that Borel set D. So the first inequality tells us that the exponential decay rate of this probability is at least as large as the distance between the theta and the closure of the set D when distances are measured with respect to the rate function I. And the lower inequality tells us that the decay rate of this probability is at most as large as the distance between the true model theta and the interior of the set D, again, when distances are measured with respect to the rate function. Now, this is a bit difficult to parse quickly if you see it for the first time, so it's best to look at an example. So imagine that we study our Newsvendor problem, and the demand has just 3 different possible probabilities. Let's assume the estimator of the demand is the empirical distribution, which is a probability vector with 3 components, and it will therefore have realizations that range over the blue probability simplex shown on this slide. We can also visualize as a red dot here the true demand distribution, which is not known to us. And then we can ask the question, what is the decay rate, or what's the probability of the yellow event, the yellow set D? What's the probability that the empirical distribution falls into this yellow set? Now, in the Newsvendor problem, the data was i.i.d, and therefore the empirical distribution converges almost surely to the true distribution. That's just the law of large numbers. And if the true distribution is not in the set D as shown here, then it's clear that the set D will eventually have probability 0. However, now we can say more. So the empirical distribution is actually known to satisfy a large deviation principle with some rate function. And therefore, it tells us that the probability of the event D decays exponentially, precisely exponentially, at a rate that is given by the distance between the true demand distribution and the set D. So the probability that the estimator falls in D decays to 0, but exponentially, precisely at the rate R. So that's the intuition of a large deviation principle. Okay, so now I'm ready to state my first main result, which is shown here as Theorem 1. So let us assume that we would like to solve the restricted meta optimization problem, where we use estimators that satisfy a large deviation principle with a rate function that satisfies certain regularity conditions. I'm not going to talk about them, that's too technical for the moment. Now, under this assumption, I can show that the restricted meta optimization problem has a Pareto-Dominant solution, and this Pareto-Dominant solution is even available in closed form. So the optimal compressed predictor is shown here, and you can see that it has a distributionally robust interpretation. It actually evaluates the worst case of the objective function over all models theta in an ambiguity set that is determined by the large deviation principle. In particular, the shape of the ambiguity set is determined, or the center of the ambiguity set is determined by the estimator theta hat T. And the ambiguity set has the shape of a ball with respect to the rate function I of the large deviation principle, and the radius is exactly equal to the decay rate R that we impose in our meta optimization problem. So that's exactly the decay rate of the out-of-sample disappointment that we require. So this is very nice. So we have this solution in closed form. It's Pareto-dominant, so it attains the corresponding surrogate optimization model, which is a distribution robust model, attains the best possible trade-off between in-sample risk and out-of-sample disappointment, irrespective of the truth of the theta, for all thetas, and therefore in particular also for the unknown true theta. So we do not need to know the true theta to guarantee that we have the best possible trade-off. Now, in constructing this solution, we had several degrees of freedom. For example, we introduced our distribution family, and actually we could have used a different distribution family that emerges from a coordinate transformation. So I could have transformed my parameterization by some function phi, which is a homeomorphism here. So that is just a continuous bijective function with a continuous inverse. My solution shouldn't depend on the particular choice of the coordinates, right? I could also have transformed my original estimator theta hat t by some other coordinate transformation, also a homeomorphism, which is noted by psi here. And the new estimator, of course, because this transformation is bijective, contains the exact same statistical information as the original estimator. So luckily, our Pareto-Dominant solution does not depend on these parameterizations. Actually, we can leverage the so-called contraction principle of large deviations theory to show that the transformed estimator satisfies also a large deviation principle with a regular rate function. And this new rate function depends on the old rate function as well as on the two coordinate transformations. So ultimately, this means that the homeomorphic coordinate transformations, they result in the same Pareto-dominant prescriptors, in the sense that they have no impact on how the optimal prescriptor maps the raw data to decisions. So this is actually a nice sanity check and shows that we actually do something that is reasonable. So now let me go back to the full-fledged meta-optimization problem, the one that optimizes over all possible functions of the data and not just on these very simple functions that depend on the data only indirectly through the statistic theta hat t. I would like to argue to you that even this much more complicated meta-optimization problem has a Pareto-dominant solution under two conditions. First is that I have, as before, a statistic theta hat t that satisfies a large deviation principle. And the second requirement is that this statistic is actually sufficient. So by definition, theta hat t is a sufficient statistic for the unknown parameter theta if the distribution of the t training samples, conditional on a particular realization of this statistic theta hat t, is independent of the parameter theta under which we took the expectation. So intuitively, this means that if I have access to the statistic theta hat t, I would not pay anything to gain access to the full training data set, because all the useful statistical information that is contained in the training samples is already contained in the sufficient statistic. Okay? So I'm now ready to state my second main result. And I'm going to assume here that I am able to construct an estimator theta hat t that is a sufficient statistic for the theta. And I'm going also to assume that this estimator theta hat t satisfies a large deviation principle with a regular rate function. Now, theorem 2 here tells us that in this case, the full-fledged meta-optimization problem, which optimizes over all possible functions of the data, still has a Pareto-dominant solution. And this solution is actually the same distribution robust optimization model that we've seen before in theorem 1. But now we show that it is not only optimal over the compressed predictors and prescriptors, instead it is optimal over the much, much larger class of all possible functions of the data. So this result tells us that there is actually a nice separation of estimation and optimization. In order to find an optimal data-driven decision, we can first evaluate an estimator, so we can map the training samples to our statistic theta hat t, and then we can solve the distribution robust optimization model that is now hidden. So given the estimator, we can solve a distribution robust problem to find the optimal action. And this separation of estimation and optimization is indeed optimal. So for those of you who have studied statistics, you may know the classical Rao-Blackwell theorem, and theorem 2 here is somewhat reminiscent of this classical statistical result. So the Rao-Blackwell theorem says that okay, let's assume we have a predictor, c hat t, which just is an estimator for the true objective function value of a decision x. Now, let's assume that we have also access to a sufficient statistic, theta hat t, sufficient statistic for the unknown parameter theta. So the Rao-Blackwell theorem tells us that if we condition this predictor on our sufficient statistic, then we obtain a new estimator that is better than the original estimator. So we get an improved estimator. Now, first, I would like to emphasize that because of the properties of conditional expectations, this new estimator depends on the data only through the sufficient statistic, of course. Now, also, it seems that this estimator depends on the parameter theta under which we take the expectation. However, this is exactly not the case because theta hat t is a sufficient statistic. So this estimator is indeed available to us. And the Rao-Blackwell theorem proves that this estimator is better than the original estimator, the original predictor, in the sense that it has a smaller mean squared error. Now, the proof of the Rao-Blackwell theorem is ingenious, but quite short, because it just uses Jensen inequality, which is applicable because the mean squared error is a convex function. Unfortunately, we cannot use the same technique to prove our theorem too. So if we construct a new estimator by conditioning on the sufficient statistic, then we cannot find a new estimator that has a better out-of-sample disappointment. And the reason for that is that the out-of-sample disappointment is actually non-convex in the original predictor. So therefore, the proof of our theorem 2 is considerably more difficult than that of the Rao-Blackwell theorem, or at least we didn't find a simple proof. So we had to go through, we had to jump through quite some hoops to actually prove this statement. So I'm now coming towards the end of my talk. I would like to show to you several data generating processes for which we can find sufficient statistics that satisfy large deviation principles, which means that for these processes of training samples, we can actually find Pareto-Dominant solutions for our meta-optimization problem. So first, let's have another look again at our Newsvendor problem, where the historical training samples are independent demand observations, and where the statistic theta hat t is just the empirical distribution, whose components are just the empirical state frequencies corresponding to the observed training samples. Now, the Fisher-Neiman factorization theorem is well known and tells us that this empirical distribution is actually a sufficient statistic for the true demand distribution. And also the classical Sanov theorem, which is also well known, states that the empirical distribution satisfies a large deviation principle. And in this case, the rate function, interestingly, is the Kuhlbach-Leibler divergence between the empirical distribution and the true distribution. So that means that both conditions of theorem 2 are satisfied. And that means that a distributionally robust predictor will be the Pareto-Dominant solution of our full-fledged meta-optimization problem. And well, the optimal predictor is shown here. It's this distributionally robust optimization model, which evaluates the worst case over Kuhlbach-Leibler wall of radius r around the empirical demand distribution. So this attains the best possible trade-off between in-sample risk and out-of-sample disappointment. And it is consistent with the results I've shown you before. Actually, we've seen that among all the models that we studied, the Kuhlbach-Leibler divergence DRO model had the smallest in-sample risk for any fixed decay rate of the out-of-sample disappointment. And what we know now, because of theorem 2, is that the red dashed line is not only the best among all the few models that we studied explicitly, it is also the best over all possible ways how we could map the training samples to feasible decisions. So no other data-driven decision could have ended up somewhere below this dashed red line. This is what theorem 2 tells us. So this is a quite strong statement. Let me show you another example. This is finite-state Markov chains. So we look at the Markov chain, and usually Markov chains are best parameterized by the transition probability matrices. here I would like to do something different. So I would like to encode the Markov chain by its asymptotic doublet distribution. So that's just the joint distribution that two consecutive states of the Markov chain have asymptotically as time goes to infinity. So the theta here is therefore a d by d matrix. I'm going to assume that the Markov chain here is actually ergodic and that all one-state transitions are in principle possible. They have a strictly positive, although potentially very small probability. Okay, so that means that, well, we can construct a set capital theta of all possible doublet distributions. So this is a set of d by d matrices with strictly positive entries. And the first constraint just is a normalization constraint, which basically states that, well, this must be a normalized distribution. And the second constraint here says that the sum of the ith row must be equal to the sum of the ith column of this matrix for each I, where the respective sum is actually the invariant probability of state I under the Markov chain. So again, we can, if we have training data generated by the Markov chain, we can construct an estimator, theta hat t, which I here choose to be the empirical doublet distribution. So this just records how often in the training data set we see a direct transition from state A to state J. Okay, and again, it is well known that this empirical doublet distribution is a sufficient statistic for the true doublet distribution. And it is also known to satisfy a large deviation principle. But in this case, the rate function is different. The rate function here is the so-called conditional relative entropy. The formula is shown on this slide. It doesn't really matter what it looks like, but it's different from the Kuhlbach-Ladler divergence of relative entropy. So that means that in this case, we can also find the Pareto-Dominant predictors and prescriptors in our meta-optimization problem that are, however, now different than the ones that were optimal for i.i.d. data. So we see that the data generating process does have an impact on what is the best way for mapping the data to decisions. We've also studied some vector autoregressive processes with unknown drift and some scalar autoregressive processes with an unknown coefficient. I'm going a bit quickly through that. So in both cases, we could construct an estimator for the unknown parameter that satisfies a large deviation principle. These estimators, however, are not sufficient statistics. So in both cases, this means that we could actually find the Pareto-Dominant solution for the restricted meta-optimization problems corresponding to the estimators we found, but these are not guaranteed to be optimal in the Pareto-Dominant, in the full-fledged meta-optimization problem over all functions of the data. So last example, let's assume that our training samples are i.i.d, but each observation xi follows some parametric distribution function, like a normal distribution, an exponential distribution, a gamma distribution, and so on. So the list on this slide is actually not exhaustive. And what we can prove in this case, that the sample mean of the training samples is a sufficient statistic for the unknown parameters in each of these cases, and it does satisfy a large deviation principle, where the rate function I is actually the convex conjugate of the log moment generating function of a single observation. So this is a very general result known as Kramer's theorem, and this tells us that really in all these cases we can actually solve the full-fledged meta-optimization problem to global Pareto-dominant optimality. But it's also very nice that actually for different distribution families, we end up with different uncertainty sets. And this actually shows the connection between the structure of the data generating process and the optimal ambiguity set. So we see that many convex uncertainty sets that have been studied in the literature, but have been used in a somewhat ad hoc way so far, they have a rigorous statistical justification for certain data generating processes. For example, ellipsoidal uncertainty sets, as you might imagine, are optimal for normally distributed training samples. So this brings me to the end of the talk. I would like to give a quick summary. So I've argued that we should, in data-driven stochastic optimization, we could set up a meta-optimization problem that tries to find the best possible surrogate optimization models, whose objective functions are the data-driven predictors and whose optimal solutions are the data-driven prescriptors. These surrogate optimization problems, they balance the in-sample risk versus the out-of-sample disappointment. And because they're multi-objective, they try to push down the in-sample risk and implicitly also the out-of-sample risk, which is the actual quantity of interest, under every possible model, and therefore also in particular under the unknown true probability distribution. We've seen that these meta-optimization problems, they, in practically relevant, interesting cases, have Pareto-Dominant solutions that facilitate a separation of estimation and optimization. And this result was somewhat reminiscent of the classical Rao-Blackwell theorem, but much more difficult to prove. The Pareto-Dominant solutions, if they exist, have a nice intuitive interpretation. So they represent distribution robust optimization models. And the ambiguity set is a ball around the statistic theta t with respect to the rate function of the large deviation principle that this estimator satisfies. The radius of the ball has a clear physical interpretation. It is the decay rate of the out-of-sample disappointment, which we specify, and we know what it means. And these solutions are also invariant under certain coordinate transformations, which is a sanity check showing that we actually do something reasonable. So in a precise sense, therefore, these Pareto-dominant predictors and prescriptors make the best possible use of the available data. And this is some form of efficiency, which is somewhat reminiscent of a classical notion of Bahadur efficiency in statistics, which is a large error counterpart of the more classical Rao definition of efficient estimators that attain the smallest possible variance equal to the inverse Fisher information matrix. So I would like to point out that these results are very general. So they hold even for non-convex decision problems. We never used convexity here. And they in particular hold also for certain non-i.i.d. data processes like Markov chains or autoregressive processes. It is quite clear that one could actually also find similar results for higher order autoregressive processes that have finite memory by just reducing them to Markov chains or autoregressive processes into memory 1. The work here also gives some theoretical justification for distribution robust optimization models. So the shape of the optimal ambiguity set can be explained by the structure of the process that generates data samples, and the radius has a physical interpretation. This work also gives rise to new optimization models, new distribution robust optimization models, which have not been studied, and maybe also some ones that I have not shown that are still out there. And these will require new optimization algorithms, because in some cases, the resulting models actually turn out to be non-convex. So there is a need to develop new algorithms, and one such algorithm is already being proposed. That's a working paper which looks at in which we try to find an efficient solution to find the Pareto-dominant solution in the case when the data is Markovian. So this is the end of my talk. Here are the references, and the main reference is paper 3, which is available in archive, and be very happy to take your questions now, and any feedback will be highly welcome on this. Thank you very much.
Thank you very much, Daniel. Really, it was an excellent talk. On behalf of all the participants and the Informs Optimization Society, I very much appreciate this talk. Thank you. So we have a short time, perhaps a few questions. If you do have questions, please enter them in the Q&A session. There are already a few, and I'm going to read them to you, Daniel. I guess the first one, maybe we alluded at the end, can the cost function C be non-convex in X? And so if there are multiple optimal solutions, will all of them be guaranteed to have similar out of sample performance?
So yes, it's true. So the objective function does not have to be convex in X. The only thing we assume in the paper is that it's continuous in X. And it is possible that an optimization problem has multiple optimal solutions. This is more of a technical problem, but that doesn't pose any real problems in this. So the distribution robust models that are the Pareto-Dominant Solutions, these may also have multiple optimal solutions. In the end, what we need to guarantee is that, well, these solutions will still be functions of the training samples, and they need to have satisfy certain measurability conditions, but this is purely technical. So in principle, as long as we have a measurable selector, essentially, it doesn't matter if there are multiple optimal solutions.
Okay, thank you. Second question. What if the generated data are subject to noises? Will the general framework still apply?
So that's a nice question. So at the moment, we're assuming that the data is precisely observable and non-noisy. Actually, there is a paper by my co-author Bart van Parijs. He studied exactly that setting, and he assumed that the training samples are i.i.d, but they're subject to noise. And he managed to figure out that in this case, there is something similar that one can do, and the optimal predictor is still a distribution robust predictor. In this case, actually, with a Wasserstein, with an ambiguity set that is described by the Wasserstein distance, but not the original Wasserstein distance, but Wasserstein distance where we have a regularization term, which is actually from the Kuhn-Bach-Leiber entropy regularization term. So the entropic regularized optimal transport problem is actually gives rise to so-called can be solved very efficiently with so-called Sinkhorn algorithm. And interestingly, this turns out to be optimal in such a setting where the data is noisy. So I'm not the co-author of that paper, so I do not know more details about that, but there is something that just came out very recently. I think this paper was put on archive a few weeks ago.
Great, thank you. A clarification question. Does your result say that any Pareto optimal solution is a DRO, or a DRO is a Pareto optimal solution? So there can be other Pareto optimal solutions that are not DRO.
So the results state that there are Pareto-dominant solutions which have a distribution robust interpretation. Now, in the restricted meta-optimization problem, I looked at predictors and prescriptors that depend on data only through the summary statistic. So the functions over which I'm optimizing there, they do not depend on time. They only depend on the summary statistic, and the only time dependence is implicit because the statistic depends on time. Now, in this restricted problem, actually, the solution is unique. So the only Pareto-dominant solution is the distribution robust solution. In the full-fledged meta-optimization problem that optimizes over all functions, we actually need to look at sequences of functions that may depend on time. And since we're only looking at asymptotic performance measures, you can imagine that you may perturb these predictors and prescriptors at finitely many time points, and this will not change the asymptotics. So therefore, there are multiple optimal solutions, and then if you do something silly, then some of them will not have a distribution robust interpretation. Yeah, so I guess that's the answer to this.
Okay, thank you. And the last question, is there any relationship between the large deviation rate function of the estimated theta hat and the true unknown random parameter theta?
So normally the rate function needs to satisfy certain regularity conditions, which it usually does. So it can be interpreted as a distance function. And you've seen in the Kuhn-Bach-Leiber divergence case, which is the rate function that applies when we have i.i.d data on a finite sample, on a finite state space, then well, it's the KL distance between a realization of the empirical distribution and the true data generating distribution, and the KL divergence will be 0 if and only if the two objects they match. So in that sense, the rate function includes information about the true parameter value. Actually, the regularity conditions that we use in the paper, they guarantee that the estimator will converge to some function from which we can uniquely determine the true theta. So yes, the rate function includes information about the true theta. Yeah.
Great, thank you. So that was the last.
Maybe I should add, we do not assume we know the true theta because we're going to optimize over the theta, right? So this needs to be true for every theta that could be the true one, and we don't make any statements about. So we're always making sure that we only make statements that hold either for all the thetas, and that includes the one that is true one which you don't know, or statements that do only depend on the data and not on theta.
Thank you, Daniel. And that was the last question. Thank you again to the speaker and all those little excellent questions. So I would like to remind you that our second plenary talk tomorrow at the same time is by Fatma Kılıç-Karzan of CMU. And we all look forward to seeing you there. Thank you for your time.